Good morning. Today I'd like to share with you some of our research that will help us realize this vision of building trusted autonomous teammates. Specifically, I'd like to talk about some of the factors we've been investigating that affect the level of trust between humans and autonomous systems. And then I'll share a couple examples that we've been working on where we've applied these principles to the development of both algorithms and a robotic system. So let me start with a story. Many of you may have heard this story. Last year, there was a fatal accident that at the time was first of its kind. The driver of this Tesla had been driving down the highway. He'd engaged the autopilot system on his Tesla and had stopped paying attention to what was going on. Now, unfortunately, a large semi-truck pulled out in front of him, and neither the human nor the car, the autopilot, was able to react in time, and the driver was unfortunately killed. Now, Tesla came out after the accident and said that this was not something the autopilot was designed to do. This was outside the parameters that the system had been designed to operate in, and that the user manual states that a driver should always remain attentive and be ready to take over. Now, this didn't happen. The driver placed too much trust in the autonomous system and assumed that it would be able to handle circumstances that came up. And unfortunately, this isn't the only case we've seen. There have been a couple other stories in the news in the last year. Another fatal crash earlier this year involving a Tesla. And then incidents of other types. There was a woman in Arizona earlier this year who was killed. She was a pedestrian walking across the street with her bicycle, stepped out in front of an autonomous test vehicle, and the safety pilot had not been paying attention and was not able to react. So it's not surprising then that we see statistics like this one that came out of a AAA study earlier this year, where 73% of American drivers report they would be too afraid to ride in a self-driving vehicle, and 63% of adults report they would actually feel less safe sharing the road with a self-driving vehicle while walking or riding a bicycle. So given the examples I just cited, these statistics aren't surprising. The issue here is that there are some really good reasons why this development is being pushed forward, both in the automotive industry, in other industries, in manufacturing, in healthcare. We're working to build, I'm sure many of us in this room are working to build systems that can help us be smarter, faster, more effective, more efficient. But we're going to be coming up against these barriers to adoption. People won't want to use or rely on these systems in sometimes very critical mission environments where they can have a lot of benefit. So that's really what spurred the research that we've been doing into factors that impact trust. How can we as system designers and developers build algorithms and systems and robots that are more likely to facilitate an appropriate level of trust with their human operators and users? So when we started this work, we started by looking at what does it mean for a system to be autonomous? And one of the ways we think about automation or autonomous capabilities is by using a scale called the levels of automation. This was a scale that was developed by Tom Sheridan and originally applied to air vehicles, but it's since been extended to other domains. And what we have here is a scale that defines the amount of control that is shared between the human and the autonomy or the automation. So at one end of the scale, you have the human in complete control. That's the Cessna in this example here. And at the other end of the scale, you have fully autonomous systems where the human operator has no input into what's going on. And where you lie on this scale depends on what you're doing. It depends on the system. There's no right answer to where you want to be on this scale. It depends on the environment, the task, the expertise of the users. But what happens is as you move up this scale, as you add more autonomy, there's a higher probability that there's some sort of mismatch between what the system does and what the user expects it to do. And this mismatch in expectations can lead to a lack of trust. Now, what you want in an autonomous system is to have an appropriately calibrated level of trust. What do I mean by that? So this graph comes from a paper by John Lee. I like it because it describes the relationship between the trust here on the vertical axis that the human operator has in the system and the capability of the automation, or the trustworthiness, on the horizontal axis. And what you want is for trust to be well calibrated. You want to be right on this line where the trust in the system is equal to the capability that the automation has. Above this line, you end up in situations like the Tesla example, where the operator places too much trust in the system, leading to misuse of the system or relying on it for things it wasn't designed to do. And below this line, you end up in a situation of distrust. This is where the capabilities that could be provided by the automation aren't realized because the operator leaves it on a shelf or in their footlocker or in a closet. And all of the benefits that could be realized are not. It may actually lead to lower performance overall. So what I've been working on is trying to capture these factors that can influence the level of trust that an operator has in the autonomous system. So to kick off this work, we started by looking at the academic literature. How is trust built? How do we understand what trust is? How is trust built either between two people or between people and robots? And we combine that with firsthand data we collected from a variety of operators. In this case, we talked to pilots of remotely piloted aircraft, autonomous ground vehicles, autonomous underwater vehicles, and discussed the factors that impact the level of trust they have in the system. And what we came up with was this set of 7 heuristics, or design principles, that capture the types of information that an operator needs to understand about a system and how that information should be communicated in different cases. So these are things like visibility of current system behavior, or what is the system doing right now? Visibility of probable system behavior, or what is the system going to do next? Can we make sure it's predictable? Transparency of failure. So if something goes wrong, does the operator, first of all, understand that something has failed, and then can diagnose what's going on? And accessibility of system rationale, which is what I think is the most interesting, in the sense that this is, why is the algorithm making decisions the way it does? And it's often hard to do with system developers. One example that came up recently was at Draper, we were looking at how can we use deep learning to infer vehicle speed from only a camera sensor. So this could be applied to autonomous cars, it could be applied to small UAVs. But how can you use only the data coming in from a camera to figure out how fast you're going? Now, one of the issues you often have with deep learning algorithms in particular is that they can seem like a black box. It's not always evident why certain decisions are being made. It's not always evident how an algorithm is coming up with the answer that it does. So one of the things our developers did was created a visualization that let us see which parts of the image the algorithm was relying on. The first attempt looks something like this. So you can see this test image here. This test image came from a simulation environment that we used to feed a lot of data into our algorithms. All of our test images had this dotted line in the middle of the road. Now, we're based up in Boston. If you've ever driven in Boston, you know that we're lucky if we have lines on the road at all, let alone dotted lines. So this is not a very robust solution. But because this was identified, we could do something about it. So the next iteration looks something like this. You can see that in here, the test images, we've removed the dotted line, so the algorithms can't rely on these features anymore. And now the algorithm is selecting a much more diverse set of features. And this is creating a much more robust solution. And in our testing, we found that not only was this a more robust solution, there was no decrease in performance. So by looking into how is this algorithm making decisions, we could ultimately design a better algorithm. The other reason I bring this up is it's so important to consider at the system design phase. So most of the time, I'm a user interface designer, and I can't count the number of times I've been brought on a project and say, okay, we've got our robot. Please build us a user interface that shows the operator what's going on. But if you haven't thought about this early in the process, if you don't have a way to get to this level of information, it's not in the API, it's not in the ICD, it's not in a way that you can get that information up to the operator, you can't build a UI to fix everything. So this is something that really has to be considered at the system design stage. All right, so now that we know what types of information have to be conveyed to an operator, how is it best to communicate this information? So when you think about interfaces for robots or algorithms, what do you think of? You probably think of screens. We build a lot of screen-based displays. We have big screens, we have small screens, we have pocket-sized screens. And this works in a lot of cases. But oftentimes, screens get in the way and could even be dangerous or detrimental to the types of interactions you want to have with a system. So what I've been working on recently is looking at how can we move away from screens and get into displays that can communicate this information in a more immersive, seamless way so that you can interact with a robot as you would with a person. So we've been prototyping a lot of these displays on the Microsoft HoloLens. The HoloLens is unique in that it's not just a heads-up display. Some of you may be familiar with Google Glass or with some of the helmet-mounted displays that fighter pilots have. And this is useful in that you can get information into the field of view. You can present information in a way that helps maintain situation awareness. But the HoloLens goes one step further. It's constantly mapping the environment, and it can display information in a way that overlays objects onto items in the environment. So I could place a visualization on this stage or at a specific point in the room, and it will stay there no matter where I look at it. So this gives us some interesting capabilities in terms of displaying different types of information in ways that might be more useful or intuitive to a person. One example is displaying sensor information. If I can collect different types of sensor information and display that information at the point those measurements were taken, now I don't have to do a mental translation between a screen to my environment. Similarly, if I want to cue someone's information to a specific point, I can now overlay specific visualizations in a way that cues me to very specific points in the room. So we've started to think about how can we use this as a way to interact with robots in a case where you might want to work side by side as a teammate. Now, the first project we've started to apply this to is an internally funded project we're working on to build a robot that can autonomously change the oil in an engine. This task in particular was chosen basically as a representative task. It has a lot of the elements that a robot will need if it wants to work in a messy, unstructured, real-world environment. Because the goal here isn't just to have a robot that could, sit in a lab in a nice isolated box and do this task. We ultimately want a robot that could work side by side, in this case, in a garage with a mechanic. And there's lots of technical challenges here. So things like being able to find objects it's looking for amongst a lot of clutter on a table, even if that object doesn't look exactly like what you're expecting. It's not the right color, it's worn out, it's beat up, it's slightly different shape. And then there's manipulation challenges of how does a robot pick up and move different objects in ways that accomplish the task. So these are all challenges that our engineers have been tackling. Now what we're looking at is now that we've solved some of these challenges, we want to make sure that we're doing this in a way that enables this robot to work side by side with a human. So what we're starting to look at is thinking about how can we communicate information about this robot to someone in a way that will help it be a trusted member of this team. So where we're starting is by looking at visualizing what the robot can see. This is a graphical representation of what this might look like. It's a little tricky to see on this display, but as the person in this case is putting each object on the table, we're overlaying graphically a model of that object. So that can indicate that the robot has not only seen the object, it's recognized it and understands the general orientation. So this is a first step, but this is what we're starting to use to prototype being able to expose to a person what the robot can see, some of the capabilities and limitations of the robot. So if you see that the robot sometimes doesn't recognize funnels, maybe that's an indication that we need to update some of the robot software. It's also a way that we can start to think about how a person might step in and help a robot. There will always be unexpected cases that we can't handle, and being able to say as a robot, I don't understand, I need help, is actually a really hard problem as well. So I'll leave it there for today, but where I want to leave you is that those of us who are designing and developing these systems, these algorithms, this autonomy, we have a responsibility to make sure that we're building these systems in a way that facilitates appropriate levels of trust to the operator. Specifically, high performance by itself is not sufficient. We really need to think about how we can help a user understand how these algorithms are making decisions. And finally, I would challenge each of you to think about how to present this information in a way that facilitates seamless collaboration and teamwork. Thank you.